Welcome back to Bite-Sized Breakthroughs, everyone. Today we're diving into a fascinating paper exploring the application of large language models for reinforcement learning. Joining us is Dr. Paige Turner, lead researcher on this project, and Professor Wud Spectrum, a leading expert in the field of AI. Dr. Turner, tell us about the main focus of your research.
Thanks, Alex. Our research aims to address a crucial challenge in applying large language models, or LLMs, to reinforcement learning, or RL. Traditionally, researchers have relied on either expert demonstrations to train these models or computationally intensive gradient methods. We present a novel approach called in-context policy iteration, or ICPI, that effectively avoids both of these limitations.
That's intriguing, Dr. Turner. Professor Spectrum, from your perspective, what are the limitations of the traditional approaches Dr. Turner mentioned?
Well, Alex, collecting expert demonstrations can be incredibly laborious and time-consuming. It also restricts the model to performing at the level of the experts, which might not be ideal for pushing the boundaries of performance. Gradient-based methods, while effective, can be computationally expensive and slow, especially for large models. This often restricts their applicability to tasks requiring quick learning or adaptation.
So, Dr. Turner, ICPI aims to address these limitations. How does it work exactly?
ICPI cleverly leverages the power of in-context learning. This means that the LLM learns from a few examples within a prompt, without requiring extensive training or parameter updates. We essentially use the prompt itself as the locus of learning, iteratively updating its content based on the LLM's interactions with the environment. Imagine it as providing the LLM with a set of instructions that it constantly refines through trial and error.
Could you elaborate on the role of the prompt in ICPI? It's not just a set of instructions, right?
Absolutely, Alex. The prompt is carefully crafted to induce two key components within the LLM, a rollout policy and a world model. The rollout policy guides the LLM in planning future actions, while the world model allows it to predict future rewards, terminations, and states. We achieve this by providing the LLM with examples of past trajectories or sequences of states and actions drawn from the agent's recent experience. This experience is stored in an experience buffer, which the LLM uses to learn patterns and make predictions.
That sounds quite complex, Dr. Turner. Professor Spectrum, how does this approach compare to existing methods for using LLMs in RL?
It's a significant departure from previous approaches, Alex. Most methods rely heavily on either expert demonstrations or gradient-based fine-tuning. ICPI, on the other hand, forgoes these approaches, relying solely on in-context learning. This allows for faster learning and adaptation, as the model doesn't need to update its parameters. Furthermore, ICPI utilizes a model-based approach, where the LLM learns to plan using a world model, as opposed to model-free methods that directly estimate value functions. This makes the logic behind the LLM's decision-making more transparent.
That's a clear distinction, Prof. Spectrum. Dr. Turner, you mentioned the LLM continuously refines the prompt. How does that actually happen?
ICPI implements policy iteration, a common RL technique, through this prompt-based learning. The LLM essentially estimates the Q value for each possible action, which represents the expected future reward for taking that action. This estimation is based on the LLM's rollout policy and world model, which are both shaped by the prompt. The action with the highest Q value is then selected, leading to an improvement in the policy. This iterative process of Q value estimation and policy improvement is driven by constantly updating the prompt based on the LLM's actions and the environment's responses.
So the LLM is constantly learning from its own mistakes and successes, improving its policy through the prompt. That's fascinating. Let's delve into the experiments, Dr. Turner. What kind of tasks were used to evaluate ICPI?
We evaluated ICPI on 6 illustrative RL domains, Alex, each posing different challenges. These included navigating a chain, ignoring distractors, solving a maze, catching a falling ball, shooting down aliens, and controlling a point mass. Each task had a specific state representation, reward structure, and potential hints incorporated into the prompt format.
6 tasks with varying complexities. Did ICPI perform well across all of them?
Yes, Alex, ICPI effectively learned good policies across all 6 tasks. We measured the agent's performance using a metric called regret, which indicates the difference between the agent's cumulative reward and the optimal reward. ICPI demonstrated low regret on all tasks, which shows that it was able to learn efficiently and generalize to unseen states and actions.
Impressive results. Prof. Spectrum, what do you think about the performance of ICPI compared to the baselines used in the paper?
It's quite remarkable, Alex. ICPI consistently outperformed all three baselines: no argmax, tabular Q, and matching model. The no argmax baseline learned a policy through random exploration and then imitated it, while tabular Q is a standard tabular Q learning algorithm. The matching model, on the other hand, used the trajectory history to make predictions. The fact that ICPI surpassed these established methods highlights its unique ability to generalize from limited experience and learn progressively, rather than relying on specific state action pairs.
Dr. Turner, did your research also explore the impact of the LLM's size on ICPI's performance?
Yes, Alex. We compared different LLMs with varying sizes and training data. Interestingly, we found that only the largest model, Codex, consistently demonstrated learning across all tasks. This suggests that model size plays a crucial role in the LLM's ability to handle complex RL tasks. It's a strong indication that future, even larger models might achieve even better performance.
So while ICPI shows great promise, are there any limitations that you observed during your research?
Certainly, Alex. ICPI's current implementation is limited to discrete state spaces. Extending it to continuous state spaces would require significant modifications to the prompt engineering and rollout generation processes. Furthermore, the accuracy of the LLM's predictions for future rewards, terminations, and states greatly influences ICPI's performance. This limitation might hinder its applicability in complex and highly stochastic environments. Finally, while we tested ICPI on simple domains, further research is needed to validate its effectiveness in more complex and realistic RL tasks.
That's a thoughtful assessment, Dr. Turner. Prof. Spectrum, what are your thoughts on the future directions of this research?
There's significant potential here, Alex. Future research should investigate the scaling properties of ICPI with respect to model size and the complexity of RL tasks. Exploring strategies for applying ICPI to continuous state spaces would be crucial. Additionally, incorporating prior knowledge and expert demonstrations into the prompting process could enhance ICPI's performance in complex domains. Furthermore, combining ICPI with other RL techniques, such as value iteration or model-free methods, might lead to synergistic improvements.
These are promising avenues for future research. Dr. Turner, what are the potential broader impacts and applications of ICPI?
ICPI has the potential to revolutionize diverse fields, Alex. In robotics, it could lead to robots that learn complex tasks through observation and interaction without needing extensive programming or training data. It could also create more intelligent game AI that can adapt to changing game conditions and learn from player behavior. In resource management, ICPI might be used to optimize resource allocation based on historical data and predictions. Furthermore, it could contribute to developing personalized learning systems that adapt to individual student needs and intelligent systems for healthcare, such as those used for disease diagnosis, treatment planning, and drug discovery.
Those are exciting possibilities. Dr. Turner, Prof. Spectrum, thank you both for sharing this groundbreaking research with our listeners. It seems that LLMs are rapidly expanding their capabilities, and ICPI offers a promising approach for applying them to RL in new and innovative ways.
It's our pleasure, Alex. ICPI offers a more efficient and flexible approach to RL, potentially opening up new avenues for using LLMs to solve complex problems across diverse fields. Indeed, this research underscores the exciting potential of combining LLMs with RL. It's a testament to the rapidly evolving landscape of AI and its ability to tackle increasingly complex problems.
Thank you both for joining us on Bite-Sized Breakthroughs. Be sure to check out the paper linked in the show notes for more detailed information. Until next time, keep exploring the world of AI with us.